So now that you're a little bit more comfortable with equatorial and axial positioning, we can actually start to talk about the stabilities of these two positions. So a lot of the times in OChem we like to talk about stability, and this equatorial and axial positioning is really no different. So for these two chair conformations, we actually have two different orientations for the methyl group. In one, we have the methyl group in an equatorial position, and in the other, we have the methyl group in an axial position. And it actually turns out that one of these positions is energetically more stable than the other. So one's going to be preferred over the other. So the question is, should we put the methyl in an equatorial position, or should we put it in an axial position? Or more specifically, what's the molecule going to do? It's going to choose the easy way out, and that's going to be the most stable position. So the way we can rationalize this is, again, trying to shrink ourselves down to the size of the cyclohexane ring. And we're going to try to look along a carbon-to-carbon bond. So this is going to be our little eyeball, and we're going to look along this carbon-to-carbon bond, and we're going to do the same thing over here. We're going to have our little eyeball, and we're going to try to look along this carbon-to-carbon bond. Okay, so what we're going to do is, now that we can look on that bond, we can draw a little Newman projection. So for the molecule on the left, if we look down this bond, Hc is, from our perspective, in a down position, and then Hb is kind of coming over here. So this is Hb. And then on the left right here, we have the rest of the cyclohexane ring kind of, floating off into space. So that's going to get kind of complicated, so we're just going to kind of ignore it for now, a little squiggly line. And so then on the other side of the bond, we're going to have this carbon with HA pointing in an upward relative position, so this is going to be HA. And then the methyl is going to be pointing to the right and down, so this is our equatorial position, so this is our methyl, or CH3 group. And then again, we're going to have the rest of the cyclohexane ring kind of going off to the side, down and to the left, so down and to the left. So I'm just going to simplify it by making these little squiggly lines, so we don't have to really worry about it. So let's do the exact same thing for the right-hand molecule. I'm going to redraw this guy, which is kind of redraw the groups, since we've gone from an equatorial down to an axial up. So again, from this perspective, HC and HB really aren't that different. We're going to have HC going down, and then we're going to have HB kind of going up and to the right. We're going to have that HA going down and to the right, HA right here, and we're going to have the methyl, the CH3, going up. So right now, it doesn't look like there's a whole bunch of difference. The part of the molecule that we're really trying to focus in on is the CH3 part. So for the molecule on the left, we actually get a full picture right off the bat of how that CH3 and what it's surrounded by. So if you look at the CH3, we have a gauche to a HB, so HB gauche, and we have this HC gauche. Okay, so these gauche interactions aren't the best, but the hydrogen's pretty small, methyl's pretty big, but it's not really clashing up against anything very large. The molecule on the right, however, we definitely get to see one of the gauche interactions that this CH3 has, and that's going to be to an HB. So that's not really any different than this gauche interaction right here, but we're actually missing a little bit of information about the other gauche interaction. So what is this other gauche interaction? So we don't quite see it at this moment, so we have to include a little bit more about the cyclohexane ring. So let me color in a little bit. Again, this green right here is the carbon that's in front, so this green is this green. And so what we did is we said that we were just going to ignore the rest of the cyclohexane ring, but now we have to fill it in a little bit more. So the group that's immediately to the left is going to be this orange hydrogen, or this orange carbon, and attached to that orange carbon are going to be two other hydrogens. One's going to be, an axial up, and the other is going to be an equatorial down. So this is a hydrogen and a hydrogen. So eventually what we can do is we can get rid of that little squiggly line, and we can acknowledge the fact that we're going to have this orange carbon. And attached to the orange carbon, we're going to have two hydrogens, and we're going to have an axial and an equatorial hydrogen. So we can draw one in, and there's one kind of going into the background, so I'm just going to kind of draw it in. Not really any stereochemical designation, but that part really isn't that important. The fact of the matter is that we have a carbon with a gauche interaction to another carbon, and that's this orange carbon. And if you had to, weigh the lesser of two evils here, you have a carbon, which is a relatively big wrecking ball, interacting with another big wrecking ball. Very high type of unstable interaction. So one very high high energy interaction and one very low energy interaction. Versus on the left, we have two very low energy interactions. So overall, it looks like the conformation on the right has a little bit extra energy that we really don't want. And so the takeaway story is that it looks like this axial positioning for this methyl right here, and again, this red methyl is this red methyl, and this blue methyl is this blue methyl. And this result is a little bit counterintuitive sometimes, but it looks like this axial position is actually a less stable position than the equatorial position. Sometimes people see the equatorial and they think that it has a little bit less room, but it turns out that the axial actually has a little bit less room and a little bit more unstable interactions than the blue possibility. So the takeaway message is that if you had to choose, or if the molecule had to choose between putting a group in an axial or an equatorial position, the equatorial position is the more stable position.